Good morning. This is your stats sensei, Mr. Spensei, and we're going to go over scenario 3 for the test review. And this is going to be a paired distribution, so we need to be careful about it. So, investigators at the U.S. Department of Agriculture wish to compare methods of determining the level of E. coli bacteria contamination in beef. Two different methods, method A and B, of determining the level were used to each of 10. That's going to be important. That sounds like that's probably going to be our sample size randomly selected specimens of a certain type of beef for more than 1,000 liters of contaminated meat. Those differences are normally distributed. That's good to know because if we have a sample size less than 30, we need to start off with a normal because central limit theorem will not apply. The data obtained in millimicrobes per liter of ground beef for each of the methods are shown in the table below. All right, so we have the data here. So test an alpha level of 0.10 to determine whether or not there is a difference in detection methods. Oh, that's another key word. Didn't say less than or greater than, it just says difference. So let's take a look at this. We want to define our parameter. Let mu d equal the true population mean difference in detection methods. And we have to select an order. And I'm just going to go method A minus B. That's the order I'm going to go in. All right. So this is interesting. Our hypothesis, of course, being a paired is just going to be mu D, mean of the differences, equals 0. And our alternative will be mean of the differences, and it's going to be 0 as well. But in this case, they just wanted to see if there was a difference. They didn't ask for direction. When they ask for direction, we need to do a couple more things. All right. So our conditions, the first condition, random sample. Well, they told us it was a random sample, happened to be a random sample of size 10, and that happened to be given. Number two, we need to know that that differences are independent because it's a random sample. Differences are independent. Number three, we need to check that n is less than 10%. In this case, our sample size is 10. We always have to multiply by 10, and that's 100. And up here, they told us that there was more than 1,000. So it looks like our population was about 1,000. So that's less than 1,000. So we've satisfied the less than 10%. So we're good there. And the next thing was it was a normal differences are normal. And that was given. So that was also taken care of. All right, our formula. Well, it's a t statistic, which is always set up x bar minus mu s divided by the square root of n. But since we're working with differences, we need to put some d's on it. So here we go, drop some d's on it. All right. What is this going to look like? Well, we're going to be centered at 0. Then I have a problem. I don't know what my x bar is. And remember, this is two tails, so I need to look at both tails. Well, I've taken the time and I've entered the data into the calculator. So we have L1 is method A, L2 is method B. We said based on the way we define our parameter, we're going to go A minus B, so second 1 minus second 2, and we get those values. Now, I have comparison values, and if you want to check stat calc 1 var stats goes second 1, and sure enough, I have a standard deviation of 8.0154, so I entered that data correctly. Then I go stat calc 1 var stats and go second 2. And I end up getting 8.3341. So that matches. So that's good. But what I'm interested in is the X bar when I do L3. So let's see what we get. Stat calc 1 var stats, second 3. Then I end up getting a 0.29. Well, that's a positive 0.29. So that's here on the upper side. And we need to shade this way. That also means that I'm going to have one that should be equidistant on this side. And really, technically, that would be at negative 0.29. But we're not going to label it because this is the one that we came up with. So our mean, we're plugging in, we have 0. We just calculated a 0.29. And we have an N, a sample size of 10. And I looked, and I have a standard deviation of 0.6297. And I'm making sure that I run the test with that. Well, remember, when we are doing the plug, if it's a two-tail, we're going to have to multiply by 2. So 2 times the probability that t is greater than 0.29 minus 0 over our standard deviation of 0.6297 divided by the square root of 10. So let's take a look at that. Stat, test, t-test. We need to make sure data is highlighted. We have a mean of 0. We're entered in L3, so second followed by the number 3. We need to make sure we have not equal highlighted, and we press calculate, and I get a t-statistic of 1.45. So once again, because this is a two-tailed test, 2 times the probability that t is greater than that 1.4562 gives me a p-value of 0.1792. All right, so my p-value is 0.1792. They'd given us a significance level or an alpha level of 0.10. And 1,792 is definitely larger than 1,000. So we're going to fail to reject. All right, so we're failing to reject the null. I want to do something else real quickly. I'm going to go ahead and run this real quickly just as a one tail and show you something. So stat test, t-test, and let's do it as a one tail upper tail. And I get a p-value. I get the same t-statistic of 1.4562, but my p-value is only 0.8964 because that's only this upper part. Now, if I take that 0.08964 and I multiply it by 2, what do you know? I get that 0.1792. So that's why we have to multiply that by 2 so that we actually show it. So in conclusion, our p-value is 0.1792. Our decision, we fail to reject the null. All right. There is, be careful here, we failed, so there is not sufficient evidence at alpha equal 0.10 to suggest that the true population mean of the differences in detection methods method A minus B. Now, what did we say is different than 0? All right, I need to make a quick change up here. This should say mean, and I left off 2 words, of the differences. All right, so make sure you're saying mean of the differences. That'll become clear in our next unit when we're working with 2 samples. All right, so we failed to reject the null. We couldn't tell that there was a significant difference. There is a difference. All right, there is a difference. We know method A detects more, or it appears to detect more, but it's not significant. It's not, we can't say for sure because it's only slightly. It could have happened by random chance alone. All righty. Appreciate you watching, and I sure hope to see you on the next one. Thank you.